let me know when you've got me on. I'm still half asleep after a bit. Alright, okay. Alright, Shubers. Right, anyways, new board. I've just started, well, I started wiring it up. I did test it earlier. There's no shorts or anything. Let me just mute my sound. Get my preview window probably up because for alignment things. Right. Well, anyway, the stuff that I stuck the heatsink on, I stuck a bit on the bottom to anchor that thing into the board, and it's sort of hardened and set now, so that's good. And the heatsink is all mounted up, and just to show you comparison, the new board with the old board, let me just move that back a bit. Right, this is the new one, there's the other board, and the built before. You can see, let me see if I can get this, hand this back a bit, actually. Oh, there's wires in the way, which is typical. Right, so that's the previous one. Previous one is the dark brown, and the new one is the light one, which is this one. So you can see that they look almost the same, except that this one's got extra trimmers in, and they're also like blue, white and blue trimmers, whereas that one's only got two. So you can see the differences. And also I didn't need that extra capacitor which normally goes down here. On this one I actually put two power supply capacitors, one over there. Well, on this one I only needed one, really. I decided just to try it with one because they're both connected across the same power supply rail anyway. So, and my test points are in as well. So if you look at this one, there's this new one's got a test point over here, and it's also got a test point over here. It's kind of hard to see. It's the white things. Right, so there's a test point there. Test point there. That's for the oscilloscope to lock. Actually, this test point, and there's that capacitor for it because of all the modifications I did. It's basically the same, but this one works at a higher frequency as well. Whereas the previous one had the output test point, but it had no test point for the scope lock thing, the trigger circuit. So this one obviously had less function. That's the main reason I built a new one, because there was a lot of modification I wanted to do. I'm going to attempt to get, well, I'm going to get the oscilloscope on. I did find out, I did do a quick test on it, this new board is much more efficient. It's much easier to tune and balance, and there was no smoke, no, because the protection that's in there would not allow that to happen anyway. Even if there was a dead short of the output, it wouldn't happen because of the protection. So it's I should have a no smoking sign on the heatsink that says no smoking, because it didn't. So yeah. Anyway, let me just get this wire connected up, because right, where's the wires? Right, oscilloscope need to be connected to ground, which is this connection, and the output goes to that test point, and the trigger for the oscilloscope goes to that point. and the power goes to there. And what else is there to connect? Because the rest of it's mostly the coils, and I've already connected those up. Obviously, seeing the oscilloscope would mean I have to change cameras. Okay, well, I'm going to have to change cameras, probably, because if I tilt this camera across over there, everything's going to be, you're going to be looking at this at a funny angle. So I am going to see if I can change the cameras over. Just give me a minute. I'm going to have to switch the camera to the desktop and then plug the other one in. I don't know if I can do that though, because actually it might not. I don't know if it'll work if I unplug the USB and swap it straight over. It might not detect the camera unless I stop the stream. Oh, it's going to give me a fit because I'm not using Manicam. Oh, damn it, that won't work. No, I'd have to stop the stream to swap the camera. No, I'll try and show you the scope. I'll try and move my lamp or something. Sorry. Right, I'm just going to have to jiggle this a bit. Got wires tangled up. Okay, let me just see if I can get this to point at the oscilloscope, because this lamp's a bit lazy. Oh yeah, it might work. Right, I'll have to get the focus adjustment on this as well, so let me just get the focus set, because this camera does have a focus on it. Let me just twiddle a bit. I don't know which way to go. What's the other way? Oh. Well, it's not as clear, this camera, for some reason. I'll try and get it nearer to the scope. Because that's what we want to be looking at, isn't it? Isn't it, I think. I haven't put the power on yet, but let's just try and lower this, because this lamp is on stilt things. Right. Let's see if I can move it closer. Ah, that's better. Right, I need to lift that lamp up a bit. Hold that one. I'll have to turn the light out. Let me just try it with the light out. Right, focus again. I don't know if I can get this focus right, but that actually it's not very good with the light out. Right, I'll go and put the power on. Right, there's the waveform. I'll try and get this light off it a bit because it's too bright. adjusting the focus right now. It seems to be best about there. Right. At the moment it's reading 0.516 AC volts on the output. I'll speed up I'll slow down the time base a bit, and that's where it's tweaked at the moment. It's much better balanced now. You probably can tell from the previous waveform that we've got equal numbers really on the top and the bottom. So we've actually got 3 up the top of the peaks. We've got 3 of the off states, which are the flat lines. So I'll disconnect the output cords with the switch. You know, I was telling you about why I wanted to put the switch on the circuit board. This is why. When I push the switch, it turns off the coils and the voltage on the output stage drops completely. We're just getting square waves more or less, and that's the waveform right now. I'll try with a magnifying glass. I don't know if it'll help focus this better, but let me just try and get this to which way to show up a bit better. But that's with the coil turned off. Where the hell am I? Stop moving. Right, the coils are turned off right now, so we've just seen the output of the extra piggyback waveforms that have been carried on the square waves. So what you're seeing is basically 2 frequencies with another frequency superimposed on the first frequency. So each section on here is 1 cycle of the lower frequency, and the little small spikes that are on it are the other frequency, which are riding on top of that one. So we're actually seeing 1, 2, 3, 4 other cycles per single cycle. So we're actually seeing 4 to 1 frequencies. Now I'll put the coil back on. You can see that the spikes are caused by the reactance of the coil. So now the coil's back on, and the output comes back as well. I'll try and turn this around a bit. It's not very easy. There we go. That's actually, oh, it's better than before. Well, that's the voltage on the AC output coil. Yeah, well, the noise will go away when I turn the coil off, because the coils are not being energized. But the output will still, you'll still see the output. Yeah, the mic's about what? It's actually, there's actually wires that pass by the. Let me just check the audio because I'm not sure. Oh yeah, well, it's picking up on the mic the wires that are trailing. Oh yeah, well, it's picking up on the mic the wires that are trailing past the microphone. Yeah, it's not too bad. Now, I mean, if I change the frequency, you'll see the output actually drops, because it's getting the right frequency as well. So if I trim one of my ports, let's trim the lower frequency. Oh, let's trim the high frequency end. You'll see more of the little peaks on the bigger waveforms. And if I move this, you'll see that also the output actually drops as well. So we're actually increasing the number of small high frequency cycles on top of the low frequency right now. And now it's beyond audible human range probably. But the waveform, that's what the waveform looks like now. That's zoomed in. I made it bigger so you can see it better. Oh, sorry. Well, you shouldn't be able to hear it. It's still coming through the speakers. What? You can still hear it? Oh. Oh yeah, a little bit, yeah. Oh yeah, a little bit, yeah. Well, that's the frequency, the main frequencies, rather than the high frequencies, which you can see better when I zoom right in like that. Which you can see better when I zoom right in like that. That's just one waveform. Now if I mix the input with the output, that's the output. You'll see the input and output together now. The output is the smaller wave in the middle, and the input is the bigger wave. There's actually quite a bit of strobing going on with this waveform, even in real life. So, regardless of what the camera says, I mean, the camera is probably telling you the truth actually. So, I'm muting myself again. Right, so we're actually seeing some kind of a strobing effect going on. That's with both signals. Now let's put the scope setting to mix. That's mix, or add. It's set to add right now. That's with the output. Both outputs on add. And that's without. That's with dual. That's just output, and that's just input. It's interesting about the voltage and current relativity, because when I switch the meter over to current, we actually get more current with this waveform and lower voltage. So if I go put this into current. We're actually at 17.5 milliamps. Now remember the previous board, when I made the previous board, we only got a maximum of 9 milliamps. I didn't see anything above 10 milliamps. I can actually get this one up to something like 22 milliamps, which is double what the other one was doing. Let's see if I can get there. Well, it's a bit iffy there, but it's around about 19 milliamps right now. But to be honest, if I go too far, it actually draws too much current, and that the objective is to keep the input current down. So I don't want to be drawing too much current. I want to be producing more output, but I don't want to be producing more output at the expense of using more input. So I'm backing it up again, and that seems to be Well, it actually seems to be a bit better around about there actually, because the waveform's increasing as well. We're hitting the resonant frequency. When you hit the resonant frequency of the waveform, the output goes up. The output in current goes up. Sorry, voltage. I'm getting mixed up. My protection circuit kicks in if I actually draw too much current, which is really what it's supposed to do, without blowing anything up. And it basically just resets, and when I bring it back into with its tolerance levels, because I'm not at a point where I want to sacrifice anything on here. I just don't want to be. I don't want to be blowing up transistors because money is tight right now. So it's actually showing 13.3 milliamps output right now. I'll put this back on voltage. We should be able to tune it back up to half a volt again. You know, about half a volt there. I'm sorry if it's annoying you like a dentist drill, but that just happens to be the frequency of my coil, the resonant frequency of my coil, and there's not a lot I can do about that. Sticking capacitors across it will only draw more current anyway, so it's not gonna. That's not going to help. Yeah, keep the kids away, yeah, that's for sure, yeah. Yeah, it seems to work better at that frequency. About half a volt AC. Thanks, Shubus. Well, it's not that audible. The only reason you're hearing it is because the microphone is right next to the wire. Let me move the microphone. Actually, the microphone seems to be holding the wire. Just a minute. Let me just find the best place for the microphone. Oh, that's worse. Oh, that's worse. Hang on. Sorry. Is that better? Is that better? The wire's tangled up. I'd have to untangle. Oh, I see where the wire goes. Just a minute. I'd have to untangle. Oh, I see where the wire goes. Just a minute. Well, if I move it under the chair, the microphone. Right. That should help. That should help. Okay, yeah, now, yeah, I've got what you mean. Yeah, I read between the lines. Yeah, it's just really getting the microphone away from the wires, that's all. It's just picking it up from the wires. I can't hear it that much. I have to struggle, actually. I have to put my ears to it to hear it, because it's not very loud at all for me, but well, I'm happy that my circuit's working, so I've got a decent tunable circuit now, and I can actually let me just adjust this lock. Oh, it's actually the trimmer wants to adjust a bit more. I can actually adjust the duty cycle much more easily. Now, if you watch this little peak here, this peak here, I can shift that peak across to one of these two peaks here. Now, if you watch that, it's twiddly, it's very fiddly, but if you watch, you'll see it move. If I go the right way, oh, it's jumping a bit. I've lost my lock, just a minute. Oh, shot it now then. I can't quite get to it now. I can move those peaks from one to the other. If I don't lose my lock, you'll be able to see it. There you go, I'm moving one peak over to the other side. But I tend to lose my lock and it wobbles a bit. If I turn it back, it subtracts one peak from the other. Now we've only got one peak at the bottom, we've got four at the top. Now we've got, that's about, when it's balanced, it works a lot better. So I'll just tune that a bit more. We should get an even balance. And when it's balanced properly, we get higher output actually. Oh, Z's on. Yay! So it's just fine tuning really to get it really balanced, because I don't have a phase lock loop on here. Brown cow. No, I've just got pink cows around here. So basically the best tuning is to get it so that you get the highest output. But anyway, as I say, when I build a new device, which is what's the next stage, it's gonna be much better coupled. This isn't coupled too well actually. I think I've only got about 10% coupling on this. It's just not a very good coupling for the output stage. I need a lot more laminations my magnetic switches need to be improved a bit more, because I've got two of them here, right? I should explain. Right, here's my magnetic switch, right, with the magnets. Oh, I've lost the magnet on there. Right, at the moment I have, oh, can you see that? I don't know if I'm on camera or not. No, I'm not. Well, the host camera. Right, at the moment I've got a huge void between my magnetic switches, right, which is and the coupling is determined by the space, the lack of iron in between the two halves. So that's on one side you've got the actuation coil, which is the primary coil, let's say over here, which is triggering these magnets, and it's actuating the magnetic field on these magnets, right, which triggers the magnetic field on the opposite side, which goes to secondary. Well, at the moment I have got too much decoupling between the two halves, really. I need to be able to influence the magnetic field a little bit more on the other side. Right, well, I'm not influencing it very well because I've only got a 1mm bridge between the two. That's in the current coil design. Well, the new coil design, instead of just two of these laminations, that's 2mm basically, 0.9mm thick is each one, and there's two of them in there. Now, instead of having just 6 pairs of these, actually 6 pairs on each side, we're talking about something like 24 pairs, or maybe even 30 pairs. A lot more laminations. Well, it's going to cost me more money to have more laminations cut because I need to have a lot more made. So obviously, and also my bridges, I'm going to have my bridges a little bit thicker, so I'm going to have a possibly 3mm bridge between the two halves. Alright, instead of 1mm. I need to increase it by 3 times, so that the actual steel comes higher up to that, across those magnets. And once I get that done, I'll be able to influence the switching much more effectively. Right, well, that's the mechanical part that's holding me back right now, and it's just all money. I mean, I'm probably going to need about 100 quid probably to get this. Well, it's going to be more than that because I've got to get the 3D prints made. That's going to be like, I've got another 2 lots of 3D prints to get made. So there's the bobbin, then there's the magnet holder. So we're talking about 30 quid for that. Then we're talking probably another 60-70 quid for the laminations, and then there's the magnets. So yeah, I think I'm going to be somewhere around about £120 in money, and I just can't afford that right now until this flipping probate comes through, and I'm just sick of it. I'm really sick to my back teeth of waiting for that. Right, let me just get this tune back up to where it's supposed to be. I have to twiddle it out, get this back up to 1/2 volt. Well, I think it's the other one I need to trim a bit. Just need to get that. Right, we're getting back up again, back up to 1/2 volt. I've actually had it higher than that. Bear in mind we're only drawing about 50 milliamps right now, 45 milliamps to drive this circuit. And it's very stable. It's very stable once you get the right resonant frequencies for the coils. As I say, I can turn the coils off like that, and we can see the differences without the coils being on there. I can't see the chat right now. Well, Alan, I was starting with a smaller bridge simply because you can always add a bit more material, and it's a lot of hard work to start filing material off. And I was working with an unknown factor. I mean, let's face it, magnetism is very mysterious, and I wanted to start with optimal decoupling. Really, it was a test for load factor. So when you load the secondary down, you don't see much of an impact on the input. Well, that's what I'm seeing, and that proved the point to me that I am getting extremely good separation, because all I saw was literally 100 microamps. That's 100 microamps is 0.1 of a milliamp difference on the input. So when I shorted the output down, and I even put a 10 ohm resistor across the output, all I was seeing was 0.1 of a milliamp difference on the input, and that proved to me that this circuit does work. Now my next phase is to start incrementally because there's something else that you might not be aware of, but when I get them other laminations cut, I can still use my existing laminations as well, and with a bigger gap, so I can actually attenuate the strength of the switching by putting alternate laminations in with a big gap and other laminations with a thicker gap, so I'll be able to tune it just like a core in a transformer, where you attenuate how much core material is in the transformer. I'll be able to attenuate the switching by the number of cores which are switching steel with the bridge between the two halves. So I can attenuate that bridge by having laminations with a bit more steel and other laminations with less steel, so I can actually be able to slide them in and out and try them with different combinations. So nothing that I've already had made is going to get binned, because I can still use them. I might have to trim some down, but I'm not going to worry about that at this point. Let's just tune this a bit more. Alright, look at we're up to, well, we went up to 5.2 volt, sorry, 0.52 volts then. I've got a slight discrepancy in my duty cycle which I need to correct, so I'm just going to adjust that as well. When you get the duty cycle set right, it should go back up to 0.522, sorry. Get too much out of alignment, then it drops like a stone, which is what you expect. So I basically counted the peaks. Let's turn the coils off a minute. Actually, I'm not seeing peaks on the top at the moment, which is interesting. Possibly because I'm not quite in phase So let's get this, let me just get this centered a minute. Right, there we go. Now let's adjust it from this point. So 1, 2, 3, 4 and a half. Well, let me just move this over. Oh, wrong one. Oh, the other position. Right, so we count the waves. 1, 2, 3, 4 and a half. 1, 2, 3, 4. I need a half on there. There's a quarter or a half. It seems to oscillate if you're not getting. Don't forget the coilers are disconnected right now, so we're actually seeing what it looks like without the coil on, and you can see how our duty cycle is changing, how one half of a wave is moved from the top to the bottom. Alright, you can see how I'm moving that duty cycle. Alright, I'm losing my lock. Wrong one. I'm doing this with the coils turned off because it's easy to do it. Yeah, well, I am making a bit of a guess measure, yeah, because I mean, as I say, mathematics is not my subject, and there's unknown factors. Right, 1, 2, 3, 4. 1, 2, 3, 4. I need to count the square bits. 1, 2, 3, 4 and a half. 1, 2, 3, 4. That's a little bit off. Right, I'm going to switch the coil back on. Oh, I went pressed the wrong one, just a minute. Right, I need to get my frequency back. The right frequency for this. My resonant frequency, where is it? It's a high one, I need to move. So once you get the duty cycle bang on, you see more equalised waveforms on it. I'm going too high there. When it's properly balanced, it's very, very stable. There's a slight offset because of the actual time. You see, when you have 1, 2, 3, 4.5 cycles on that carried on that other waveform, obviously what we're dealing with is time as well, because the time base. So when it drops, because of the time passing, the actual peaks that we see at the bottom, they might not be equalised. You might actually have more of one of these at the bottom because of the fall time. You've got fall time and rise time. So if one of these peaks is chopped off at the start of its descending, fall time of the thing, then it's going to be added to that fall time. But if the actual peak on the next rise time, if the next spike happens in the middle before the rise time, then you will see a different result at the bottom. It depends if the actual beams actually collide and actually intersect at the same point. So that's why it's so difficult to get these waveforms to balance out properly. It's just a bit like two people throwing a ball at the same time. You can't really measure the you can't easily measure the mass or whatever. It's hard for me to figure it out as well. What happened to Z? He came in, he said brown cow. Maybe he's going live in a bit. I'll have to check. There's nothing on there yet. I don't know what brown cow means. Oh, my leg, I've got trouble with my leg. Oh. I've only had 1 cup of coffee since I woke up, so I'm going to make some more coffee, okay? I'll leave that at that for now. But I'm only driving this at about, hang on, just a minute, I'll double check. Actually, I've got 18 volts going into this right now, and it's much more efficient than what previously. Yeah, I need coffee. Oh dear. I feel like I've been sleeping on a bloody rock all night. It's getting cold. Winter's coming. I don't know if I'm waking up or falling asleep, but well, for the fact that I've just got out of my bloody bed, I would think the contrary. So yeah, it'll be a lot more fun when I get the new device to actually produce some energy. Something that I can put through a rectifier. That's what I want. Well, I can't do that with this one because there's not enough laminations. But I am working on a budget, so I can't remember what reading what I had it set up before, but right, let's check this. Turn the high frequency back down again. Well, it definitely works better at the lower frequencies. So we're back up to 0.5 volt. We definitely work better at 0.5 volt because the current consumption, from what I can see, is actually lower as well. Actually, I need to measure the input current. I need to get my meter in line. If I've got an extra crocodile lead somewhere lying around. But then work at where would I put the flipping meter? Would it show up there? No. Could I stick it on the side? Maybe. I need to find another lead somewhere. I'm measuring the current on the supply current to the whole circuit, right? But it's across the other side of the room, and it's an analog. It's an analog meter, so it doesn't give me exact readings. And oh, that's seal lead. Right, I'm going to interrupt power a minute. I'm going to stick this on milliamps, 200 milliamps. I'm afraid the meter's on its side. I need to connect. Oh, what the hell? Where's this white yellow wire come from? Oh, I've got another one. Ah, I didn't see that one. Am I still, everything's still connected up, yeah? Right, okay. I need to connect that one to ground. No, actually, I'll do it to positive. I'll connect that one to positive. Right, we should see current on the meter. Is it on DC? Yeah. It's actually reading, which is what I thought, 41, 42 milliamps. So it's about the same as the previous device. It's actually consuming. If you remember the previous test with the previous board, we were actually consuming about, it was around about 42 milliamps, wasn't it? If I remember rightly, yeah? Well, anyway, this device is putting out more, really, and a little bit more. it's working better, but it's still drawing the same amount of current. Now what I want to show is the difference. Now if we're looking at this meter, what happens when I turn the coils off, right? Right, now I'm going to disconnect the coils on this by pushing this switch. Now that is the current that the circuit's using without the coils. Okay, that's the reason I put the switch in there, because we can see how much current the actual circuit is using without actually powering the coils. So the circuit is using 36 milliamps. So the difference is the amount of power that is being used by the coils, right? So 36 milliamps for the circuit, right? 36. Subtract 36 from 42, and it is 42. It's hovering around 41.9 or whatever. Well, subtract 36 from 42 and you get the actual amount of power that's going into the coil, right? That is the number that we need to use, because obviously there's optimizations that can be done to this circuit, such as driving this circuit with CMOS. There's things like using a regulator that's CMOS, and there's all kinds of things that could be done to build a circuit that's more efficient, that doesn't use as much power. So we have to discount that, the amount of power that's being used by the circuit, because it's a variable that can quite easily be modified. But the ultimate variable that cannot be changed really is the amount of power consumption by the coil, other than changing the frequencies and finding its resonant frequency. So we need to subtract 36. Oops, I didn't press it properly. 442. And I can't add, so I'm going to have to get my calculator. But that's what's going into the coil. Right. No, yeah, we subtract 36 and 42. Yeah, that's right. Let me just work this out. 42 minus 36. I can't add today. I just can't. I'm half asleep. 6 milliamps. Holy crap! So my coil is using 6 milliamps of energy going in. Both the coils. Oh wow. So I'm literally putting 6 milliamps in. Yeah, well, at some point I need to build a really more efficient driver circuit, that's for sure. But I mean, obviously I could probably use CMOS, but then I can't use a 556 anymore, because they have a very the drain current on a 556 is actually 10 milliamps, and the source current is 100 milliamps. They can't sink very much current. That's the problem with using a CMOS version of a 556. They can't sink very much current. That's the big problem with those. So there's other options out there. There's other circuits which I could probably design and build, but I really don't want to be going that route yet. I really want to get the mechanical side sorted out, because at least I know what power in I have going into the coil, which is 6 milliamps. Okay, I could put that on an AC and measure that as well, but there's no point. You get a more accurate reading on DC anyway. You get a smooth DC signal, so for measuring current on DC it's a lot easier to subtract and do a little bit of math on the amount of power that's differential power. Because you remember the circuit, all we have is a switch here. We have a switch here which actually interrupts the output between the output decoupling capacitor and the output coils. So when we switch it off, all we're doing is disconnecting the output from going to the coils. So we are still reading the input current, right? We are still reading input current, which is 36 milliamps, and we disconnect the output. So the circuit. Oh, sorry, a stretch. Anyway, I'll turn my meter off because I don't want to run the battery down. It's not really changing much at the moment, unless I do something. And Alan's in and out. That's fine. That's fine. I've got chores to do as well, to be honest, but I can't do them in the middle of the night. I can't do them in the middle of the night, and I'm not going to do either. I need to hoover up as well. Yeah, we have equal peaks now. We have 4 at the top, 4 at the bottom, which is good. It's a lot better than that other circuit board, that's for sure. Because last time it was uneven. I had down like 3 or something at the top and 4 at the bottom, and yeah, it was a mess. But at least that's straight. Stick this back on current again. The voltage is dropped to give it actually. Oh, that's because it's going through my meter. The meter's there's some losses in the meter, obviously. Let me just go directly to the coil again. Right, we're going direct to the coil. Oh yeah. Right, if we watch, that should go back a bit higher. Oh, it hasn't gone that much higher. That's weird. It was at 5.5 of a volt. What have I done apart from changing the? Oh, that's strange. Oh, yeah, there's a wire loose somewhere. Well, that's interesting. Hmm, 0.495, and all I've done is move some wires around. Yeah, we're probably getting a certain amount of biofeedback, well, not biofeedback, but I just moved the trigger wire a bit higher. See what happened when I took the trigger off? It just went wild. At least the trigger circuit's working. So the 100N that I used for the output for the external trigger on the oscilloscope, that works really well. I am so glad that I didn't have to stick a 1 microfarad capacitor electrolytic in there, because that would have meant polarity issues. And this polyester 100N is just right. I wonder what Z's doing. Is he going to come on, or is he having his tea? Let me think, what time will it be? It'll be 9 o'clock, 10 past 9. Where's Z's? He's probably watching the Late Show or the news or something, or doing online research. I'll switch the coils off again. That's the waveform without the coils on. The output disappears. I'll put the beams back onto dual. Hang on. Oh. Well, that's dual. Now switch to output only. That's output. That's channel 2 output. channel 1 input, but obviously the volts scales are different on here. I can turn the output 1 up, and input dual, and this is add, this is on add. It looks like on add the phase is about the same, which is kind of cool. I'm fascinated on the dual setting how we get these tiny little ripples like strobing. I don't know if you can see them, but right, well, if Z's about, I've got a spare circuit board. I'll be happy to make him a circuit board of this circuit and send it to him anyway, because I'm sure he'll have fun playing around with this, because he's got all kinds of he's got all kinds of motors and things which he could try tickling with this circuit, I'm sure. And it should be capable of driving higher currents as well because of the heatsink design I've put onto the board. And obviously it could use thicker heatsink as well, and actually some copper plate. I was thinking about this myself. If I wanted an even better heatsink, I could go on eBay and you can actually buy some copper sheet which is like 1mm thick, be about the same thickness as this steel, and I could make a heatsink out of copper instead of steel, because it would conduct the heat much more effectively. So this particular board could be easily adapted to run higher currents. That's why I've made it like that, so that I'm using tip 41s and tip 42s, tip 41C, tip 42C, because they're capable of delivering, each transistor is capable of supplying 6 amps, right? So each output stage, well, added together, they will be capable of providing somewhere in the region of what, 10 amps I would have thought maximum, with suitable heat sinking. But I'm not going there. I don't want to go there myself. I want to work with minimal input. I'm trying to do this with a reference input of about 50 to 100 milliamps, and the reason for that is because I'm comparing the results that I get with this solid state version with the rotary one, the rotary motor that I was using to drive my rotors, because I want to compare the input, which was on that one, that motor was about 100 milliamps, wasn't it? It was about 120, 130 milliamps to drive the motor, to turn the rotors, to drive the actuation. Well, I'm trying to actually get the same output. I want to get the same output and the same voltage and current coming out with less input going in. So if I can do that at 100 milliamps or 50 milliamps, and I actually get the same actual voltage coming out, or even higher voltage coming out and higher current coming out, then it will convince me and make me much happier that I'm steering away from the rotary design, because the rotary design's got other issues like drag on the rotors with wind and friction, bearing friction, the weight of the rotors, and then there's all the other problems that you have with noise and you know, and size as well. So there's that issue as well. I mean, keeping this compact and small is one of the main things that I'm trying to focus on as well. So that is why I want to keep my input on the circuit board below 100 milliamps, because I can use that as a reference and direct comparison, you see. But if I start going above that, and I start going into what, 2 amps, 3 amps, 4 amps, I'm lost. I am totally lost, because anything I get coming out isn't directly relatively comparable to any previous tests that I did. Alright, I need to shut the stream down, save this as a file, otherwise it's going to get lost in the ether with all the other long 3-hour videos without a title. So I'm gonna save it as SSD version 8. Actually, this is version 10, really. Yeah. Oh well, I'll save it again as version 8 for now, because I made some more tweaks to my PC, my circuit and all that, but I haven't actually etched that board. So yeah, it's still version 8. Anyway, let's save this file.